All right, welcome everybody. Thanks for being with me here today. This is my talk on ephemeral cloud infrastructure for acceptance tests with TFE, which is Terraform Enterprise, and GitLab. My name is Wes Novack. I am Director of Platform Engineering at Pluralsight, the technology skills platform. Before I dive into my talk, I want to acknowledge and recognize my team. This is my platform engineering team. We've got Parker, Jason, Chris, and Brett. So many of the things that I'm covering in this talk, a lot of the innovation, the patterns that we've put together are, the team is largely responsible for this. So I want to give credit to the full team for all of the great work that they've done in this space. So to describe our team and what we do, and also to talk about our company a little bit, the platform engineering team is an internal service team, and we serve the greater engineering organization at Pluralsight. So at this point, Pluralsight is a mid to large size company. We have over 50 product experience teams, so 50 product development teams. And my team, this team here, is tasked with serving those teams by providing tools, packages, libraries, systems, other useful things that help our majority of our engineering teams do their jobs easier, get things done, not have to reinvent the wheel. We want those other product teams to be able to focus on their core mission of delivering wonderful experiences to our customers. So a lot of times that manifests for us as shared libraries and packages that we provide, and that's what we're going to be talking about in this presentation as well. So to start with the problem, we had stood up a Vault cluster, or a few Vault clusters inside of Pluralsight, and then we created some packages for both .NET and for Node to allow for our teams to more easily integrate with our Vault clusters. And we wanted to know, how do we test our .NET and Node packages in real-world environments, the same compute environments that our customer teams will be using those packages and libraries in. So what we came away with was the pipeline that we're going to be talking about in this talk. But first, I wanted to talk about those Vault clusters. So inside of Pluralsight, my team owns the Vault clusters that we've deployed, and we have really just two primary environments there. We've got our staging Vault cluster and our production Vault cluster. And we run our acceptance tests directly against our staging cluster in the staging environment. So speaking again to the desire to want to run our acceptance tests in these real-world environments, to have confidence in our code changes before we publish new versions of our libraries and packages, we targeted the three most popular compute environments that our customer teams in the Pluralsight engineering org use. And those compute environments are shown on the screen here. So we've got Amazon EC2 virtual machines. We've got AWS Lambda functions as a service. And we have Kubernetes, where many of our teams are deploying, and many of our teams are shifting over to Kubernetes. So that is one of the more popular compute platforms that we have now, and gaining more and more steam within the organization. So how did we go about creating this pipeline that uses ephemeral cloud infrastructure to run acceptance tests in all of these three different real-world compute environments? We leveraged GitLab for our CI/CD solution, and Terraform Enterprise for our infrastructure as code and remote run execution environment for spinning up and tearing down those ephemeral cloud objects. So looking at the GitHub repository for our libraries and our packages, this screen here is a representation of what that might look like. So you might be wondering, why am I showing GitHub when I just talked about GitLab? Well, we still use GitHub for our source control. So all of our code goes into GitHub, and then we set up projects in GitLab that mirror the GitHub repositories over to GitLab, which then kick off our CI/CD pipelines. So for our Vault libraries and packages that we provide to our customer engineering teams, this is what a repository might look like. We've got some app code directories that contain the source code in TypeScript or C#, depending on if it's a Node or a .NET library. And there will be multiple directories, of course. And then we'll also have these Terraform directories, as shown below, that will contain the definitions of our infrastructure as code that we will use in our pipelines. So you can see under Terraform, we have two subdirectories. We have one we name static. And as we were exploring this space and figuring out how to go about this and architecting this, we quickly found that we couldn't or we didn't want to put everything inside of our on-demand Terraform scope, which is the location where we define those ephemeral objects that we spin up and spin down with every run of our pipeline. So we came up with this concept of a static directory that is a long-lived directory in terms of the cloud objects that it creates. And one of the reasons for this pattern and splitting it out is that there were a lot of different permissions that we needed to enable to create some of these objects in the static directory. So we create things like a Vault role and things like a Kubernetes namespace. And we didn't necessarily want to figure out how to inject all of those different permission sets and credentials into our Terraform Enterprise workspace where those remote runs happen. And we also had some dependencies and some prerequisites that we create here in static that our on-demand scope depends upon. So an example of one of those things is the IAM user that we create. We create an AWS IAM user. We create a set of access keys. We define all of the permissions for that particular user and those access keys. And then after we create them in this static scope, we inject those directly into our TFE workspace so that when we do the remote runs for spinning up and tearing down our ephemeral cloud infrastructure, that TFE remote workspace has all of the permissions that it requires to manipulate cloud objects in our AWS accounts. And again, in this on-demand directory, that's where these ephemeral objects live. So really, we've got things like the EC2 instance and the Lambda function defined here in this on-demand Terraform scope that we spin up and spin down on every invocation of our CI/CD pipeline for these acceptance tests. So after talking about Terraform, there are two other files in our repositories that I absolutely have to mention that are key to our continuous delivery pipelines here. And that is a make file and a .gitlab-ci.yaml file. So that make file, I'm going to talk about more here in a few of the subsequent slides. But for the GitLab YAML file, let me just quickly mention that GitLab as a CI/CD service has this concept of pipelines as code. And so you use this .gitlab-ci.yaml file to define exactly how your pipeline will look. You define the stages, you define the different jobs, you define the logic that you want to run in those jobs. That all exists here in that .gitlab-ci.yaml file. So moving on, GNU Make or GNU Make. This is an open source utility. It's commonly bundled in many of the Linux distributions. This was originally created to help with compiling and building and installing software on systems. And it allows you to wrap different chunks of logic into these rule sets and into make targets. So even though it was maybe designed to be used for software building and installation, we found that GNU Make was very useful for us to encapsulate the logic of our CI/CD pipelines so that we could really minimally define any logic inside of our GitLab YAML file. We moved all of that logic over to this make file so that we could quickly invoke those using the make utility. And then it also allows us to run these CI/CD jobs and that logic that would normally run in our pipelines. We can also run that locally on our developer machines as well. So moving over here to the next slide, this is a tree output of one of our repositories to give you a look into what some of the files might look like in our PS Vault node package repository. And I split this into two different sections here to fit it on screen here. So you can see that my kindergarten art there is showing that the tree structure continues from the left back up there to the right side of the slide. But to highlight a few of the things happening here in our repository, we got that make file. Again, that is key to the pipelines and our processes here. And so the make file is directory dependent. And if you are running a command, a make command from the same directory as a make file, then it will look for the targets in that make file to determine what commands and what process to execute. And inside of a makefile, inside of our targets, we often make calls to some of our other shell scripts that also exist within our repository. So you can see an example here up top. We've got an aws-run.sh shell script, and I'll talk a little bit more about that later. Over here on the right, we also have another helper script named tfe-run.sh. And again, I will talk about that later, but just know for now that we've got we've got processes defined in our makefile that also makes use of calling some of these other shell scripts, some of these helper scripts that wrap some things that help us with our pipelines. So moving on, here on the screen, I've got a section of our makefile, so you can take a look at what a makefile might look like if you're not familiar with it. At the top here with this big emblazoned red arrow, we've got this EC2 target. So makefile, again, the core concept here is that you have targets inside of your makefile. In this case, I have an EC2 target in my makefile. And in this particular case, this EC2 target is calling many other targets within the same makefile. So if I wanted to execute this EC2 target, I would go to the same directory as the makefile and run make space EC2. And so again, you can chain these make targets together, and that's what we're doing with this EC2 command. So for example, we've got this EC2-download-zip make target that is going to be invoked if you call that make EC2 target. And then if we look a little bit further down the file, you can see that the EC2-download-zip target has a bit more logic inside of it. So it starts with a log, and then it calls a bash shell and invokes our aws-run.sh shell script. And then it passes some parameters to it. If you've used the AWS CLI, you will recognize that this is an AWS CLI command to call S3 and copy a zip file from an S3 bucket down to a /tmp directory on a local file system. So to explain what's going on here a little bit further, this aws-run.sh shell script is really just a wrapper script for us that helps us call this AWS service called Systems Manager. So AWS has this service called AWS Systems Manager, and you can install the AWS Systems Manager agent on your EC2 instances, and that enables you to be able to run remote execution commands from anywhere to your EC2 instance, as long as you have the proper IAM credentials to do so and permissions to do so. So this script, again, really just helps us call that AWS Systems Manager run command to be able to do remote execution on our EC2 instance and run some commands as part of our pipeline to prepare that EC2 instance for the acceptance test that we want to run on top of it. And in this case, again, we're copying a zip file to the temporary directory on the instance so that we can do things with that later on in the pipeline. So moving on to another section of our makefile. In this section of our makefile, we have two targets. We've got a make target named tfe-apply and a make target named tfe-destroy. And in these two make targets, we are also running a log command, and then we are also calling a bash shell, which invokes our tfe-run.sh shell script. So again, this is another helper script that we have that we keep at the root of our GitHub repositories. And this particular script is really just a wrapper around some curl commands that we use to invoke the Terraform Enterprise API. And so you can see some of the parameters and things that are getting past that shell script. And as you might imagine, what this script does really is it allows us to trigger the Terraform Enterprise workspace to do a remote run and spin up our ephemeral infrastructure and then tear it down or destroy it when we're done with it so that it's no longer running. And we can do that inside of our GitLab CI/CD process due to the makefile and these helper scripts that we use. All right, so let's move on and talk about GitLab, which is the glue that holds all of this together for us. GitLab is our CI/CD solution here. And again, as I mentioned on one of the previous slides, we've got this .gitlab-ci.yaml file, which defines your pipelines as code. So at the very top of your GitLab CI YAML file, you normally have a definition for all of the stages in your pipeline. So there are two main things that you have within a GitLab pipeline. You've got your stages, and then you've got your jobs. And you can have multiple jobs that run in a particular stage, and you can have those jobs run in parallel or concurrently in the same stage. And those stages are often dependent upon each other. So if one stage fails, then maybe the rest of your stages don't execute and your entire pipeline gets stopped. But a lot of that is configurable. So moving on to another section of the GitLab pipeline as code file. In this section, you can see that we have 3 different jobs defined. These jobs are named lambda-acceptance-tests, EC2-acceptance-tests, and K8s-acceptance-tests. So 3 different jobs that are defined, but all 3 of these GitLab jobs are defined to run in the test-acceptance stage of our pipeline. So all of these jobs will run in parallel and execute once we reach that test-acceptance stage. And this is the part where we kick off our acceptance testing for our library code or our new package code and ensure that everything is working as desired in these 3 different real-world compute environments. Looking at the script section of these jobs, you can see that the logic here is very simple. It's just a call to make. So again, we're leveraging that make file to encapsulate the vast majority of our logic. And then here in the CI/CD pipeline definition, we can just have a simple command to call make Lambda or make EC2 or make K8s. And those correspond to targets in our make file. So this is nice, again, because it moves all of your pipeline and job code into a location that is decoupled from your particular CI/CD solution. So it would be easier for you to migrate from one CI/CD solution to another. But for us, it also helps us to be able to run these make commands on our local developer workstation and replicate what happens during the CI/CD pipeline locally as well. Moving on to another part of our GitLab-ci.yaml file, you can see here we have 2 jobs defined for infra-up and infra-down. You can also see that the stage here, or the stages for these jobs are named the same as the job. So that's fine. You can name a stage and a job the same thing. And in this case, this one job is going to run in that stage that is named the same as the job. These 2 jobs, I should clarify. And then if we look at the script section of these jobs, again, not much logic here, right? Like we're putting all that logic inside of our make file. And so again, in the script section here for the CI/CD pipeline definition, we can just make a simple call to make. And in this case, we're doing a make tfe-apply in the infra-up job. And in the infra-down job, we're doing a make tfe-destroy. And again, that references those make targets that we have defined in our make file. All right, so we have gone through and looked at some of those files, and now I want to switch over to GitLab and show you what it looks like, do a demo, and run through a pipeline so that we can see what that looks like. So here we are in GitLab in our PS Vault Net project inside of GitLab. I'm going to click Run Pipeline. And of course, normally these pipelines will kick off automatically when you have updates to your VCS or your code repository. But for purposes of this demo, I'm going to kick off that pipeline manually. So we can see that first stage in our pipeline is named test-build, and the job inside of it is named AWS-build. So if I click on that AWS-build job, it's going to give us the log output for that particular job. So don't mind the big blue rectangles, nothing to see here. I'm just obfuscating some of the more sensitive details that might appear in some of our pipelines. Whenever you kick off a job, you've got a GitLab runner that has to prepare its environment. So that's what we're seeing here, where there's this initial process of getting that GitLab runner prepared for executing all of the logic inside of your job. So we can see here, this job produced an artifact, it uploaded an artifact, and then that job succeeded. We actually run our GitLab runners on Kubernetes infrastructure inside of our private networks in AWS. So that job succeeded. If we go back to the pipeline, we're on the infra-up stage of our pipeline, and you can see that there's 2 jobs in this stage, and they're executing concurrently. There's this infra-up stage that is going to spin up our ephemeral cloud infrastructure. And again, for us, that means an EC2 instance and a Lambda function. We're going to upload our, after we get those created, we're going to upload our new code changes to our library and then run our acceptance tests in those real world environments. Here on the logging screen, again, you know, the runner was preparing its environment. And then now we can see that the runner successfully made a call to Terraform Enterprise. And if we tab over here to Terraform Enterprise, we can see that there was a remote run that was triggered from GitLab. And I've sped up this video to 15x. So you can see that that's flying along there, and that we had a plan that finished. And then from our GitLab pipeline, we confirmed that plan. So then the apply started running. And then eventually 3 minutes later, that apply will finish and we'll have our EC2 instance and our Lambda function. So spinning up a Lambda function on a VPC can sometimes take quite a bit of time. So that Terraform Enterprise remote run completed successfully. If we tab back over to our GitLab UI, looking at our pipeline, after a minute or so, it will detect that that infra-up job completed successfully. After it continues to query Terraform Enterprise, then we move over to this test-acceptance stage of our pipeline. So in this test-acceptance stage, we've got, again, these 3 different jobs that are running acceptance tests. We're going to click into the Kubernetes acceptance test job. And we're going to see what happens when we run these acceptance tests inside of our Kubernetes environment. So as you can see from that previous screen, this stage has 3 different jobs running concurrently, one for EC2, one for Lambda, and one for Kubernetes. So after the GitLab runner is initialized and prepared, it starts executing the commands that are defined in our GitLab CI/CD pipeline definition. That makes, you know, a make command call, and all of our logic that's defined in our make commands starts getting executed. And in this case, you can see we're doing something with our Docker image layers, creating a Docker image. And once the Docker image processes are completed, then we essentially take that image and deploy that image. First, we push it to our image registry. We use Harbor internally here at Pluralsight. And after that image gets pushed up to Harbor, then we do a deployment into Kubernetes using a raw Kubernetes manifest. Once that's deployed, it quickly does its set of acceptance tests. And here on the screen here, you can see that those acceptance tests have run, and we have 0 failed tests. By looking at that line 301 on the screen, we've got an empty array there of no tests that failed, and our job fully succeeded. So if any tests did not pass, then the overall job would fail and it would halt our pipeline. So those tests pass. If we tab back over to our GitLab CI/CD pipeline, we can see that the EC2 and the Lambda acceptance tests are still running. They take a little longer. And then eventually those EC2 acceptance tests pass, the Lambda acceptance tests pass, and now we've entered the infra-down stage of our GitLab CI/CD pipeline. So if we click into that and then we tab over to our Terraform Enterprise UI, you can see that there was a destroy that was triggered by GitLab. So again, our GitLab pipeline is going to call the proper make target. That make target uses our TFE-run helper shell script to make an API call to Terraform Enterprise to run a plan for a destroy. And then once the plan is finished, we make another API call to Terraform Enterprise to confirm that plan, and then we run an apply. And you can see in this case, our apply finished successfully, destroy in this case, and our EC2 instance and our Lambda function were torn down because we no longer need them. All of our tests have run. So tabbing back over to the GitLab pipeline, you can see that infra-down job has now completed successfully and our pipeline has finished. So that is the full picture and the full story of our pipeline that spins up infrastructure to run those acceptance tests and then tears it down after those acceptance tests are done. So I'm going to jump back over to my presentation and talk a little bit about some of the challenges that we faced in building and running this particular pipeline and chaining all of these technologies together. So one of the challenges we've seen is that when we update our Terraform infrastructure as code, that will trigger an automatic TFE run and GitLab runs, which will cause conflicts with one another. So inside of Terraform Enterprise, when you configure a VCS, there is no way to stop changes to that VCS from triggering remote runs on that Terraform Enterprise workspace. And because our GitLab pipeline also triggers off of code changes in our VCS, that causes this conflict where multiple Terraform Enterprise workspace runs try to kick off at the same time. But that's only when we update things within our Terraform directory, because we have that Terraform Enterprise workspace configured to only detect changes inside that Terraform directory and the particular Terraform directory for the on-demand infrastructure. And when those multiple runs do occur, it can cause some pending jobs and blockages that we need to clean out manually. So when that does happen, we have to go in there and maybe cancel out some plans, cancel out some pending runs. And so it's a minor inconvenience. The alternative, and what HashiCorp Terraform recommends, is that you can, instead of configuring a VCS on your Terraform Enterprise workspace, you can simply package up all of the Terraform that you want to execute into some kind of archive and then provide that to Terraform Enterprise when you make the API call. And that's just something we haven't explored or tried to do yet ourselves. So that's one possible workaround. Another challenge is storing and accessing credentials in TFE can be tricky. Again, that's partially what led us to this pattern of having this static directory separate from an on-demand directory. We didn't want to put all of our credentials and all of the different ways that we store things also inside of this Terraform Enterprise workspace. So we didn't want to put our Kubernetes credentials and our Vault credentials and all of these other things in Terraform Enterprise, which led us to that pattern of having this separate static and on-demand set of Terraform code. And then lastly, destroying security groups associated with Lambda functions can take very long, and it can also have intermittent failures. So this is a really interesting issue that we ran into, where in the AWS documentation, the official documentation, they say that a security group that's associated with a Lambda function that's on a VPC can take up to 45 minutes to be destroyed. And so we were getting some failures in our pipeline and in our destroys, and when we were tearing down our security group that was associated with our Lambda. And so looking at that guidance from AWS, we actually updated our security groups module in our Terraform Enterprise registry to allow for it to take in a parameter for a timeout value. So even when we passed in a parameter that said, please use a timeout of 46 minutes for creating and destroying this security group that's associated with the Lambda, we still saw intermittent failures. So that didn't even solve the problem for us. So what we wound up doing there was actually moving that security group object from that on-demand directory over to static. And so that was a workaround that worked for us as well, and also sort of helped us keep that pattern of keeping those two sets of different Terraform code in those different directories. So that's all I've got for today. I really appreciate your time and you being with me. I'm very passionate about these subjects, these technologies, and these patterns. If you want to talk to me, the best place that you can get a hold of me is on Twitter. I'm at WesleyTech on Twitter. So please follow me there, hit me up there, tweet at me. And also Pluralsight is hiring. So if these technologies are interesting and you want to work with very smart individuals on bleeding edge technology, please check out our careers page at pluralsight.com/careers.